We follow a river now on schools from its very source to its very mouth in landforms.
The UK physical landscape has the reputation, rightly so, of changing very quickly in appearance from one place to the next. By world standards, the country has an amazing mixture of landforms and relief inside a very small area. The maximum variety in the minimum distance. In this programme, we're going to see one of the best examples in the UK of how landscape changes over short distances by following a river in the north of England from its source to its mouth. You wouldn't call it a famous river, but in its short 100-kilometre journey to the sea, it has some superb pieces of physical geography common to many river basins in the UK. In fact, this river is in many ways pretty special. It's the Tees in northeast England. Like most rivers in Britain, the Tees starts off in one of the most desolate environments in the country, the moorlands. In this case, the moorlands of Cumbria, not far from the border with County Durham.
There aren't actually that many rivers in the UK which start off in dramatic environments, tumbling out of beautiful rocky mountainsides. More often than not, their source is a big soggy mass like this. These areas certainly get the UK record for damp and gloom. The altitude here is about 600 metres. Temperature and sunshine figures are very low, and just over there is the crest of the Pennine Hills, which catch the full force of depressions moving in from the Atlantic. With annual rainfall at 1,200 millimetres, these bogs never dry out. They soak up water like a sponge.
For well over half the year, the moorland sponge is unable to hold on to the huge amounts of water that fall on it. It lets it go via a network of trickles and rivulets that eventually combine to become what's recognisable as a stream. This programme was shot at the end of March. On the second day of filming, the depths of winter returned in full force to the moorlands at the source of the Tees. A very active cold front swept across the crest of the Pennines. The temperature plummeted 8 degrees and 10 centimetres of snow were dumped on the ground in just a couple of hours. At this altitude, just a few hundred metres downstream from the soggy moorland summits, the Tees is still a very narrow stream. But it's already starting to cut a V-shaped valley at certain spots, and it's carrying quite a lot of sediment, the material that it's forced out of the land surface on its way down.
The sediment carried by a river is usually divided into 3 different types. Firstly, the solute load. That's the material that's been chemically dissolved into the water. Second, the suspended load. Those are the minute particles which are carried along by the river and often give the water a murky look. Thirdly, the bed load. That's the larger material, like this. Let's forget the big boulders for a minute and take a shovelful of bed load that looks a bit more average. Not very scientific, I know, but we'll compare it with samples taken from further downstream.
Like me, if you live in the southeast of England in lowland Britain, you may have no idea of just how extensive these upland areas are. In the UK as a whole, one estimate says that the moorland environment covers a quarter of the country. As the Tees flows down through its moorland section, however, it's not long before you come across the first artificial thing in the landscape, a reservoir. Reservoirs are very common in the upland sections of UK rivers. They store water for urban areas and industries farther downstream, where rainfall figures are low and water can often be scarce. The water company doesn't only control the reservoir, they also decide how much water to allow into the river at any one time. They try to imitate what would be happening naturally, and in March, that means the highest flow of the year. The Tees is now really up and running with high levels of erosive energy.
This spot is only 5 kilometres from the source of the Tees, but already there's nothing sharp left in the river. Every piece of the bedload has had its corners knocked off, smoothed and rounded by the erosion that's happened so far.
It's in this section that erosion is at its most powerful. The downward gradient plus the high volume of water and bedload have enabled the Tees to cut several steep V-shaped sections. As the river drops to about 350 metres above sea level, the wild moorland environment begins to peter out, and more space is taken up by farmland. At this altitude, practically all of it is pasture used to raise cattle and sheep. With meadows in the valley floor and the steep V-shape on the valley sides, as the river sweeps downstream in broad curves, the Tees is beginning to excel as a piece of top-notch scenery.
But of all the superb features that rivers contribute to the landscape, maybe none can match the beauty of these.
The Tees has a flow rate of 20 cubic metres a second. It's only at a place like this that you get a real idea of how much water that actually is. The High Force waterfall.
The key to the formation of a waterfall, and this goes for 90% of waterfalls worldwide, is rocks. And here, at High Force on the Tees, the river runs across a rock called Whinstone.
The Whinstone isn't just the key to the waterfall. It has some unexpected links with other geographical features in northern England. One of them is well worth a quick detour. The Whinstone is an igneous rock that squeezed its way upwards towards the Earth's surface 300 million years ago, in a very thin layer, rather like the filling in a sandwich. Once it had cooled, like most volcanic rocks, it was extremely hard. Much harder than all the other rocks in the area. So, following millions of years of erosion, the Whinstone stands above the average level of the North England countryside. This turned out to be a very useful geographical quality to a famous historical figure. His name was Hadrian, and he was a Roman emperor. On a trip to the north of England in 122 AD, he noticed that the Whinstone stuck up above the landscape, and he ordered a wall, Hadrian's Wall, to be built on it. It became the heavily guarded frontier of the Roman Empire. with a superb high-level view of any possible invading army out across the landscape to the north. Right, back to the Whinstone at high force.
So we've got Whinstone, but very important, there's the second rock at high force. And it's the difference in hardness that's crucial in understanding how the waterfall came about.
In this cross-section, the Whinstone is the darker layer of rock on top. It's so hard that the river can't wear it away. The lighter layer of rock underneath is the softer one that I've just smashed with the hammer. It gets slowly worn away by the water swirling at the base of the falls. It's pretty obvious what's going to happen. And this simple process will of course happen again and again. The end result is that the waterfall actually moves upstream from the spot where it started. As it does so, another landform is created. A gash in the landscape with very steep sides and a river at the bottom. A gorge. And a gorge is exactly what lies immediately downstream from the waterfall at high force. Not far from the falls, the Tees leaves its steep upland section and broadens out. As the altitude drops, temperatures rise. Rainfall is lower and agriculture is easier. Farmland now occupies 95% of the valley. Most rivers are at their most powerful just at the point where they leave their upland sections. The amount of energy in the river is linked to how much water, how fast it's flowing, and how steep the river's course. 95% of a river's energy is lost through friction with the bed, the banks, obstructions, and vegetation. That leaves only 5% for carrying out erosion and transporting the bedload. The sum total of a river's energy gradually declines as it moves downstream. One result is that it can't carry the larger pieces of bedload that it was able to shift in its upper section. In the middle section, the size of the fragments is smaller. Just over halfway down from the river's source, the feeling of being in a valley has completely disappeared. The lowlands of the floodplain extend for 10 kilometers or so on either side of the river. With the climate getting warmer all the time, agriculture now includes arable crops like oilseed rape. On this stretch, the Tees does another one of its classic pieces of physical geography. Meanders. Meanders of all shapes and sizes. Meanders can crop up anywhere along the course of a river, but they are always much more frequent, larger, and more curvy in the lower reaches. In the flat, lower section of a river, meanders are constantly changing their position. At this particular spot, it's possible to project what's going to happen next. Maximum erosion is on the outside of the bends, where the water is running fastest. The shape of the meander therefore develops like this. Result, the meander gets cut off, leaving a feature known as an oxbow lake. One of the Tees' meanders encloses a whole town, the town of Yarm. 250 years ago, it used to be the most important port on the Tees. It's only 18 kilometers from the sea as the crow flies.
But it was a struggle for ships to get this far upstream. There were so many meanders between the coast and Yarm that bigger ships had to be pulled by horses trudging along the towpath. But Yarm was the Tees' most important port for a very long time. There was shipbuilding and sailmaking here, and farm produce was exported to London and the European mainland.
Yarm has never made it as a modern industrial centre. For the most part, it has stayed where it always was, inside its own personal meander. What killed off Yarm's commercial future was this: a bridge built across the river much nearer the sea, around which grew up the town of Stockton. Stockton became one of the centres of the Industrial Revolution in the 19th century. In the early days of Stockton's growth, though, the town's Victorian businessmen weren't 100% happy with the Tees. There were still too many meanders between the port and the sea, a time and money-wasting problem.
The Victorians weren't exactly environmentally minded. In fact, they often regarded nature as something that got in their way. The solution, therefore, to the problem of the Tees meanders was straightforward. They chopped 2 of them off by building a brand new, dead-straight 3-kilometre channel. The original natural course of the river has disappeared. So from here, as far as the eye can see, the Tees is completely artificial.
And so is the whole of the landscape in the river estuary. These last few kilometres of the Tees before it enters the sea were once a huge marshland. In its middle and upper sections, the river was powerful enough to carry large fragments in its bedload. But here in the lower section, the river can only carry and deposit the finest material. Time for the last bedload sample.
And I think I know what we're going to get here. Estuary mud.
30 or so years ago, there was a boom in heavy industries, looking for lots of space, lots of water, and easy access to the sea. The estuary mud was dried out and reclaimed, and a whole range of new industries was developed. North Sea oil terminals, petrochemical works, a nuclear power station, and, biggest of all, an iron and steel works.
The biggest requirement for space on the steelworks site is the stockyard, where the 3 basic raw materials for steel are kept: iron ore, limestone and coal.
Even here, surrounded by the landscapes of heavy industry, things all really focus on the river. The Tees is crucial to the steelworks operation. 90% of the plant's raw materials are brought in by huge ships from locations all around the world, and the river is deep enough to accommodate them. On this particular day, the last river landscape on the Tees before it enters the sea features a 150,000-ton coal carrier from northwestern Australia. Such is the end of a 100-kilometre trip that started in a soggy mass high on the Pennine Hills. It's been 15 degrees today down here on the estuary, but someone's just told us that it snowed again up on the moors at the river's source. What did we start off by saying about the landscape along the Tees? The maximum variety in the minimum distance.
Geography teachers will be interested to know about NetNotes Plus, a new online
On Channel 4 Schools now, a cool look at the Ice Age in landforms.
middle of the 19th century, when physical geographers were really getting to grips with the forces that moulded the UK landscape, this boulder in North Yorkshire still had them completely baffled. The base it sits on is Carboniferous limestone, which is the bedrock for this area. But the boulder itself is grit from the Silurian period, which is the rock type 8 kilometres from here, in that direction. There were some pretty far-flung arguments as to what or even who moved it here. Maybe it was an ancient race of giants. Maybe it's the remains of a religious monument. Or maybe, and this was the most popular stab at the argument, it was moved here by Noah's flood. That Noah's flood could have shifted these rocks seems far-fetched to us nowadays. But at the time, there were lots of things about our landscape that geographers were only just beginning to understand. There was a country, however, that had already solved the mystery of rocks in the wrong place. With the Alps and glaciers on their doorstep, the Swiss knew all about them. 100 years ago, a Swiss geographer gave his British friend the vital tip-off. Dear colleague, your out-of-place rocks were picked up and carried by ice. Not surprisingly, it took quite some time for the message to sink in that Britain had had an ice age and that the country had actually once looked like this. But these shots, taken in present-day Iceland, are very close to the sort of landscape that Britain had during that 4 million year period when great sheets of ice moved back and forth across the country. Here in the UK, glaciation brought huge changes to the landscape, so much so that they stand out loud and clear to this very day. In this programme, we'll be finding out what some of them are. To start with, though, what was it that kicked glaciation off? The answer? Quite a list of factors. Firstly, of course, a downward trend in annual temperatures over a long period of time. Then, enough precipitation to produce enough snow. And finally, spots like this. We're in the Brecon Beacons in Wales, just about as far south as glaciation happened in the UK. The Brecon Beacons had one more vital quality that encouraged glaciation: the right lie of the land. It's that hollow sort of cup shape in the hillside over there that's important. It's north-facing, and year after year, probably for hundreds of them, the snow on the ground wouldn't melt completely during the summer. The depth would grow until the lower layers were compacted by the pressure into ice. The ice would start to flow downhill. The birth of a glacier. Those areas of the UK that had huge amounts of ice moving across them were completely transformed, like here in northwest Scotland. One of the first things you notice is that you spend an awful lot of time walking around on bare rock. Whatever soil there was here has been picked up and carried off by the ice. The boulders and stones caught up in the ice made it work like a massive grinding machine as it trundled its way along here. In places, it acted like a huge scouring pad, smoothing the rock into an almost polished surface. Often, though, the smooth bits are interrupted by these grooves called striations. They were gouged out by sharp-resistant boulders trapped at the base of the ice, and they're still here after 11,000 years. Other glacial clues here we're already familiar with. Boulders picked up by the ice from elsewhere and dropped down along its course. The correct name for the boulders is erratics. The world record for an erratic is 13,700 tons in Wyoming in the USA. The ice had amazing power,
and the results could be spectacular when the power was directed at a single valley. It seems amazing that ice can actually flow, but that's exactly what it did, thanks to the force of gravity and the sheer weight of the ice itself.
Some of the best glaciated valleys in the UK are here, near the west coast in northern Scotland, and this is one of the most dramatic. It's got a great Gaelic name, the Bealach na Ba, the Pass of the Cattle. It's got a small river in it now, but there's no doubt about what actually caused the massive gash that towers 700 metres above it. It was ice.
The glacier that occupied this valley until 10,000 years ago was one of the last to survive in the UK at the very end of the Ice Age. 10,000 years sounds like a long time back, but geological time, of course, is measured in hundreds of millions of years.
So, geologically speaking, ice was here only yesterday, and the clues in the landscape are still very fresh, like plenty of erratics, and halfway up the valley, a ledge of glacially smooth rock.
When the Bealach na Ba glacier and others in the area were in what's known as surge condition, they could move at 10 kilometres a year, an amazing lick.
And surge is what must have happened here. On its steep downhill run from the 900-metre summit to sea level, the ice gained a massive amount of power to help it grind away at the land.
Erosion in valley glaciers was carried out by two forces. First, the ice itself. Second, by boulders, rocks and stones, the ground moraine, caught up in the glacier's base. When the ice retreated from the Bealach na Ba, the glacial erosion had straightened and widened the valley, leaving a sort of U-shaped trough in the landscape. In fact, throughout the UK, shapes cut by ice have made the scenery grander and wilder. Here's a selection of UK glacial scenery, mentioning the locations and the names of the major features most often used in books. There's no doubt that one effect of ice was to produce some of our most beautiful scenery. Did glaciation, though, do anything more practical?
Well, the answer to that is yes, and especially as far as transport is concerned.
In all the UK uplands, the widening and straightening of the major valleys opened up the mountains for road and rail routes.
Here in the Scottish Highlands, this opening up of routeways in mountainous areas happened in a rather special way.
Towards the end of the Ice Age, the ice sheet in Scotland wasn't thick enough to smother the mountains that run like a barrier through the northwest of the country. In places, though, a tongue of ice did manage to force a way through. When the ice retreated, what was left behind was the usual U-shaped glacial trough. It's called a breach. There are lots of them in Scotland, and they're absolutely ideal for railways to find a nice flat route through the mountain barrier.
So, there is in fact an interesting connection between the Ice Age and the 1045 from Inverness to the Carl of Lohelch.
But although some of the most spectacular changes to the scenery happened in the mountains, the effects of the Ice Age were felt in lots of other places too. And to find out how this happened, we need to go 10 degrees latitude farther north, to Iceland. Here, only 1,000 kilometers from the UK, there are still permanent ice caps that survive all year round. It's as if the last phase of the Ice Age had never gone away.
This is the Vatnajökull, the largest ice cap in Europe. 8,400 square kilometers of silent whiteness. These days, though, you can forget about the silence for some of the time, because in Iceland there's been a useful knock-on effect of glaciation. It's called tourism.
I was lucky enough to be the first visitor of the season. The date was May the 13th, the temperature -8.
The ice on the Vatnajökull is up to 1,000 meters deep, and although it never got that thick in the UK, this is certainly what Wales and Scotland and much of England would have looked like.
The really useful thing about Iceland is you get a very clear idea of what happens not only on the ice, but beyond it. There are all sorts of different looks to the edge of a glacier. There's the giant teeth look. Then there's the meringue look. All, though, have one thing in common.
The edges of ice caps and glaciers are distinctly messy. That's because they're starting to lose their grip on all the different bits of material they've picked up along their path, like these huge boulders. So, if ever there was any need for proof that ice can carry things this heavy, here it is.
In Iceland, at the end of winter, at the edge of the ice, an event happens that occurred millions of times in the UK during our glacial period. Water takes over from ice as the main driving force. Just like a river, this glacial meltwater starts to move things downstream, away from where the ice has come to rest. As the ice starts to lose its grip, a huge range of material gets shifted along. Boulders, stones, gravel, the lot. What the ice has eroded, the water transports away. As we saw earlier, the landscapes created by the ice itself may be spectacular, but those beyond it are vast in scale. There are many different types of glacial deposits. In Iceland, one of them has a landscape all to itself, called outwash plain. In places, the outwash plains carry very little vegetation, deserts on the Arctic Circle. Here, in addition to ice and water, another force has added itself to the glacial story. Wind.
The material's constantly being moved around by the streams on the outwash plain, so vegetation never gets the chance to take root. It's also so fine that it's easily whipped up by the wind. Much further south in Europe, where the climate's kinder, dust like this has resulted in one of the most fertile soils on the continent, where it's called loess.
Ice, water, wind. The three forces still at work in present-day Iceland, just as they were in Britain a long time ago. Let's quickly summarise just how far these effects of glaciation went in the UK. The ice itself, at its maximum extent, came as far south as the River Thames. Glacial deposits left beneath the ice are the grey areas on the map. Now if we add the regions where water and wind deposited material beyond the ice, we can fill up even more space on the map. So, taking all the glacial forces into account, the result is that 2/3 of the country were affected by the Ice Age.
It wasn't just in the uplands that glaciation produced useful results like easier routeways. It happened in the lowlands too, like here in this quarry in Shropshire.
The quarry has been excavated into glacial deposits brought in by 3 different ice sheets from 3 different directions. Fragments of rock transported by the ice from hundreds of kilometres away are lying all over the place.
Just lined up a few bits here. Granite from Cumbria, Lake District ice. Limestone brought here by the ice sheet from North Wales. And sandstone, ice from Ireland. And there's another real bonus from the Ice Age in this lucky quarry. This is the local sandstone, which has been ground up by the ice right here. After it's been processed, it's sold off to the building and construction industries. The quarry's other product is 20mm gravel, as it's known in the industry. It goes straight into producing concrete, and it's wonderfully multicoloured. Conveniently assembled in this one spot, all thanks to the Ice Age.
There's a big question mark over one issue for the future. Will the ice ever come back? Well, as you can imagine, there are lots of theories, and one of them says the answer is definitely yes.
The statistics go something like this. A complete glacial cycle, that means from when the ice starts to advance to when it retreats and disappears, is 110,000 years. That cycle is then followed by an interglacial period with little ice activity, which lasts for 10,000 years, and we're now at the end of that period. In fact, just about ready for the next advance. But don't worry, with glacial science as it is today, we'll have plenty of time to get out of the way.
Geography teachers will be interested to know about NetNotes Plus, a new online service providing extensive program support, pupil for postage and packaging. Now on Channel 4 Schools, Place and People looks at the effects of erosion in landforms.
This film is about a frontier. You won't find it marked as a red line on a map, yet it's 5,000 kilometres long and runs around the edge of Britain. It's the coastline. This frontier that looks so permanent is in fact constantly changing in detail. The coastline is a battleground between land, sea, and human activity.
We often get the wrong impression of the coast as an environment, probably because we normally go to it on holiday when it's nice and warm and sunny and relaxing. But the truth is often more like today. It's 2 degrees Celsius, got a force 6 wind coming from the southwest, and masses of wave energy directed at the frontier between land and sea. The power of the waves depends largely on the distance they have to travel, and that distance is called the fetch. And there's nothing between this stretch of the south coast and Brazil, 10,000 kilometers way out there. So, what with the huge fetch from the southwest and the powerful southwesterly winds, today these two forces are working together to hit the coast really hard. I think I'd rather be on the beach of Brazil, wouldn't you?
The enormous amount of open water between America and the British Isles enables the waves to gain great power during their long fetch from the southwest. What's more, the most common wind is from the same direction, adding even greater power to the waves. One of the places that gets the full force of all of this is where this programme was made, the coast of southern England, in Dorset and Hampshire. Thanks mostly to the high wave energy, this stretch of coast has some of the grandest scenery in the country. And the shapes of the landforms are thanks to a lucky mixture of rocks, some hard, some soft.
And it couldn't be clearer. Hard rock, just a few meters away from soft rock.
The harder rock is on the outside, facing the sea. It's called Portland stone. This works like armor, protecting the softer rocks behind from the waves. But the sea is a very powerful force and always finds a way through. It seeks out weaknesses in the outer wall and drives holes through it.
Once it's punched through the Portland stone, the water eats away at the softer rock behind, creating coves and inlets.
This erosion that's happened in the softer rock behind the hard outside wall is something that's going on all along this piece of coast. In one spot, the sea has taken the process much farther and created one of South England's great beauty spots, Lulworth Cove. We can speed things up to show how the cove was formed. First, we need to whiz the clock back a few thousand years. Right. So hard rock on the outer wall, soft next behind it, then hard again behind that. Then the start of the process is the sea punching a hole through a weakness in the outer wall. Once into the soft rock, the sea starts to erode sideways and things speed up considerably until it reaches a barrier, the second wall of hard rock. Result, the shape of Lulworth Cove today. Recently, geologists have been able to apply this process at Lulworth to other parts of the south coast. They now have a much clearer picture of how large stretches of coast have evolved over thousands of years. David Harlow, Bournemouth Borough Council.
Has the coastline always been this shape?
No, not at all. This is the coastline we recognise today, from Old Harry Rocks all the way around Poole Bay to Hengistbury Head, around Christchurch Bay to Hurst Spit and to the Needles. But 9,000 years ago there would have been a continuous chalk bridge from the Needles to Old Harry Rocks. By about 6000 BC there must have been a large erosion bay forming a much larger version of the Lulworth Cove that you can see now. Probably by 2000 BC there was a very much bigger bay, and by Roman times the coast was beginning to look as it does now with two distinct bays.
Much of the time, changes to the coastline, like those described by David Harlow, happen so gradually that the process is hardly noticeable. You could sit around for months without spotting a single change.
But it can be extremely quick. The crew of the Eastbourne lifeboat saw something huge happen with their own eyes on this stretch of coast at Beachy Head.